Hi everyone, welcome to Physics Rocks It's True, and in this episode we're going to learn how to make lasers and produce X-rays. So let's get on with it. In our last video we should have learned that electrons exist within energy levels in a particular atom, which means that generally speaking an electron you'll find in the ground state, that is, that it has the lowest possible energy that it's allowed to have and is sat down here. This energy level is usually represented in electron volts and is given a negative value. So let's say that's negative 10 eV for the sake of this video. Okay. That means that I would have to give it 10 electron volts of energy in order to take this electron and remove it entirely from this atom. Okay. There are other possible states that this electron can exist in. The next one up is called the first excited state. In this case, we'll say it's at negative 5 electron volts. And then there will be other states above that, continuing on and getting progressively closer and closer together. So let's call that negative 3 electron volts. And there will be states up here as well. But this will do for now. What this means is that an incoming photon of light, get ourselves an incoming photon of light, an incoming photon of light may strike and be absorbed by this electron. If the photon of light has an amount of energy equal to a gap in these energy levels, so say it is a 5 eV electron, or a 5 eV photon I should say, if it comes in and strikes this, the 5 electron volts will be absorbed by the electron, and the electron will jump to this energy state. The photon is absorbed and therefore does not exist after this. Hide it off the screen there for a moment. Okay, now electrons don't like sitting in elevated excited states and will within a matter of nanoseconds drop back down into the ground state. Because of the conservation of energy, it's gone from negative 5 to negative 10 eV, so it has lost 5 electron volts and will therefore produce a photon of 5 electron volts that will travel upon its merry way. Okay, simple matter of conservation of energy. Now that's okay. Just to make sure that we're still on the same page, if we give this 7 eV, it can jump from 10 up to the 3. This is a little bit more complicated in this case because now we have two decay mechanisms. We can go from negative 3 to negative 5, which would produce a 2 electron volt photon, like so, and then fall the rest of the way, producing a 5 electron volt photon. Like that, as it falls all the way down. And the result is we get two photons, a 2 eV and a 5 eV. Or, depending on how the fortune favors us, it could drop directly from the 3 down to the negative 10, or from the negative 3 down to the negative 10, and produce a 7 electron volt photon. One of those options is going to happen. So either you'll get a 2 and a 5 or a 7. And our 7 eV photon will be a little bit more energetic than the 2 and the 5. Okay, so that's us pretty much up to speed on where we should be at beforehand. One important thing to note, of course, is that it is not possible for our electron to absorb, say, 4 electron volts because it can't jump to here. That's not possible. You can either jump the full way to an energy level or not at all. Okay, so in the case of, say, a 6 eV photon came here, it simply wouldn't be absorbed by the electron. It would not be possible for the electron to absorb that. Is that all right? Okay, so what we want to do is we want to make a laser. So a laser is very simply very, very, very concentrated light of a particular frequency. Right? Rather than, say, you're making white light, you've got an entire range of frequencies across the visible spectrum. Laser light is very specifically one frequency. And since it's one frequency, then E equals HF is our equation for the energy of a photon. F is a single frequency, H is a constant, which means that these are photons of the same energy. So to make a laser, each photon has the same energy. And that's the plan. Okay, that's dead simple, in principle anyway. All we need to do is get a pile of electrons across a whole material. So, and that shouldn't be too bad. We should be able to get a material that's got an energy gap that we like. And now, imagine my energy level diagram. This is not now for a single atom, but this is for a whole material I'm talking about here. So we would 1, 2, 3, 4. Say we've got a material that has 5 atoms in it. Okay, what we want to do is we want to put 5 electrons up into this 5 eV state, and then when they all fall down, we'll get 5 electron volt photons. Simple. So not just one of these, but we will in fact get 5. So 3, 4, 5. If I can do that continuously speaking, then I'll have a laser beam. The unfortunate thing is, remember what I said, that electrons don't like being up here for any particular period of time. They only sit for a few nanoseconds. So I'll get a 5 eV, and then how would I get them there? So the general way of promoting electrons within a material is to heat them, which is a good idea. That provides energy to the electrons and knocks them up into various energy states. Okay, let's imagine there's another one or two up here, just for the sake of drawing the diagram. Okay. Boom, boom. Now the problem with heating things is that you've got no great control over exactly how much energy you're going to give them. So as we can see here, we've managed to achieve 1 electron in our excited state that we want. That's going to give me a 5 eV photon, which is excellent. And then everything here could give me, well, anything. I can get a 2 EV and then a 5 EV, which would be not too bad. I can get a 7 out of that. I can get maybe, what does that look like? Maybe a 9 out of that and an 8.5 out of that. That's not laser light. It's light. Okay, that's what's actually happening when you heat something like a piece of metal. Everything just goes into random energy states all over the place, and when they fall back down, you get all sorts of energies and all sorts of photons out. So well done, we've invented a light bulb. But we don't want a light bulb, we want a laser. We want a single frequency laser. And to do that, then, we need to build something that has a little bit more of a manufactured system of energy levels. Okay? And what we want is, let's say we still want 5 electron volt photons. We take out this and we go and build ourselves a material. We find materials that help us out. And one of these materials that we're going to find has something pretty special. It's got its energy levels and all going on here. That's great. Okay. But there's a specific energy level here in certain materials that we call a metastable energy level. Yeah, these are quite difficult to manufacture, difficult to find, so you can't just do these with anything. But what a metastable energy level does is that rather than the electron falling straight back down within nanoseconds, the electron sits there, possibly for a few milliseconds, which is, you know, 1,000,000 times longer than it normally would. It just rests there for a moment and then drops down. Okay. Now then what we can do is we can do our usual fire everything up using our heating or whatever it is that we're using, you know, electrical processes or whatever. And our little electrons will fall eventually into this metastable state. Okay, some of them will drop straight back down. That's fine. But most of the time we're going to end up catching them here. It's like a little net that they're going to bounce off. Okay, and they're going to sit there for a little period of time and gather up. And then they're going to fall. Giving me 5 EV, 5 EV, and 5 EV. Now it gets better. Photons have a habit of creating other photons. Photons like being in the same state as each other. They're not particularly big fans of being out of phase and away from each other. So what happens is this. When one of these electrons drops from our metastable energy level to our ground state and releases its photon, it then stimulates other photons other electrons to drop as well. Okay, and they will fall. So if the electron can fall from the metastable state here to produce an equal energy, same phase photon, it will. Okay, and this is called stimulated emission. That these electrons probably weren't going to fall, or at least there was no great urgency in them falling until this photon came past, okay, and interacted in some way. The result was then that these were all stimulated and made to fall. The result is now, and through our filament we're going to send some current. And the result of that is that some electrons are going to be excited and removed off here, okay, especially if we make this negatively charged. Okay, so we can end up with a little cloud of electrons around here. Just like this. Make this a bit prettier. There we go. So we've got some electrons hanging around. Of course, we know that electrons are negatively charged, so there's a minus, and there's a minus, and there's a minus. So everybody's got some minuses going on. Okay, now all we have to do then is we have to accelerate these electrons and make them hit this tungsten, which is, again, relatively easy to do because all we have to do is connect our tungsten to some form of positive power supply. Okay, so connect that up to some form of positive charge and make that, therefore, an anode. For those of you who like such labels. And then this end here, we could charge negatively once we've got a few electrons off here, and we can make this a cathode if we really wanted to have some accelerating fun. Now, remember that negative repels negative and positive attracts negative, so our little electron is going to accelerate across this gap. And how much it's accelerating depends on the voltage or the potential difference between these 2 points here. Okay, so there's a potential difference. Okay, and that is the energy per coulomb of electrons. Okay, so we can actually work out how much energy is being given to every particular electron. And now do you see where we're going? Because if we know that the electrons have sufficient energy to strike into our anode here and promote our electrons in the anode up to their excited energy level. Remember the energy level that we said was equivalent to the production of X-ray photons. Then what we're going to do is these electrons are going to hit this electron, jump it up. It's not going to sit in that excited state for long. It's going to drop back down, and we are going to get out of this process an X-ray photon. That's the game anyway. And that's how it works. It's ridiculously straightforward. It really, really is. There's a couple of other ways that things occur here. That's the kind of straightforward mechanism, is that electron here comes in, strikes the electron in the material, jumps it up, and then it drops back down, producing an X-ray that flows out. There is another way of doing it. It's maybe slightly beyond the scope of most courses, but if you have a nucleus, which I will color in sort of bluey color, just to make sure that we understand that we're not talking about an electron here. The nucleus of an atom is positively charged, like that. It is possible that my electron travels past a nucleus. Okay, so it comes along like this, and doesn't actually hit an electron, but is changed direction and slowed down because of the fact that it's come screaming past and then accelerated. There's been a change of speed here, and some energy has been lost. If that energy is lost, energy can't be created or destroyed. It simply is changed from one form into another. There's no real mechanism for anything to change here because it hasn't hit this, so it can't transfer heat. It's certainly not making any sound. But what it does is it produces a photon here of energy. Right? And that photon may be in the X-ray region, it may not. And this is called braking radiation. Not barking radiation, as I've just written. Braking radiation. My German is terrible, but I think its technical name is Bremsstrahlung radiation, if I've if any native German speakers that are watching me butcher that, I'm awfully sorry. Okay, this break-in radiation also produces photons, but it's not really what we're after. What we're more interested in is this excitation thing. Okay, so that's going to produce, coming out of this, then we're going to have X-ray photons just all over the shop. Okay, not only that, we're going to have electrons that don't quite make it there with the energy, because remember, not all the electrons are going to have the energy gap that we want. The energy gap for X-rays is going to be pretty high because it's a large amount of energy to make an X-ray, as you can imagine. So there will be other energy levels in here as well that are going on. So we're going to get photons of all sorts of descriptions. We're going to get high energy X-rays, we're going to get low energy X-rays, we're going to probably get some light going on out there as well. We're definitely going to get heat because like just every time something hits something, you're looking at heat. So there's all sorts of stuff going on here. And that makes it quite difficult from a practical point of view to make it into an X-ray machine. Because if you build this thing, if your patient is here, let's put a little person here. You can see my art skills are coming along nicely. Little person. Well, that's great. They've just been zapped by this X-ray. Lovely. Unfortunately, the maternity ward is upstairs. And we've now just irradiated unnecessarily a whole pile of expectant mothers. Whilst that's ethically bad, it's also extremely legally bad for any hospital that happens to be trying to do this. So we need to refine this idea. We also have a problem that if we continue to do this over a long period of time, our anode here is going to heat up. It is a metal. It's going to keep heat in it. Eventually, it's just going to waste itself out. It's going to melt. It's going to char. It's going to do all sorts of things, which makes ourselves a whole pile of problems. But this is all now engineering problems. Physics is solved. Okay, we shoot electrons at a tungsten target. Better label that tungsten just so that you remember that. If the electrons have sufficient energy, they will create X-rays. Now we need to clear up the mess, and that's not as difficult to do as you might think. Okay, objective 1. We get our little filament. Okay, we also have a little cup here as well that runs as a cathode. And that deflects the electrons sort of into a beam. So we're just definitely shooting it at our anode target. I'll go and grab our little anode target as well, just so that we're working with roughly the same stuff as we had before. Okay, and we're going to connect that to our positive supply. Okay, so we've got X-rays going on all over the place. So first things first, we want to make sure that our electrons arrive at the target with the requisite amount of energy. So as with all things, you don't want things messing with your stuff. Stick it inside a vacuum chamber. Job done. Okay, job 1 complete. Stick it all in a vacuum. Okay, now EM radiation is absolutely no respecter of vacuums, so we are still going to get our X-rays coming flying out all over the place. Okay, so that's good news. It's going to fly out of our little vacuum thing. So we're going to surround the whole thing in lead, which you should remember from GCSE is the absolute go-to for stopping radiation of almost any form. Okay, we'll make it dark grey. Well, we're not filled in though. That was bad. Just want a line colour. That's better. Okay, stick some lead around it. Ah, damn! That hasn't quite solved our problem because now that we've surrounded it in lead, none of our X-rays are getting out. Okay, remember our patient down here. Let's grab him again because I don't think I'll be able to do as good a drawing for a second time around. So let's get ourselves sorted out here. Grab our guy or girl. We're equal opportunity X-rayers. And well, that's terrible. It's absolutely terrible. We now haven't X-rayed them. So what we'll do is we'll make a small opening inside our little problematic thing. So we'll put our little window in here that lets X-rays out. Okay, so let's get our window in here. Fill that in white. There we go. And now any X-rays that are produced can come and zap their way through here. Yay! Now, we may not necessarily want all the X-rays that are produced. We probably only want the really high energy ones because they're the ones that are going to go through the person's body. and actually onto the X-ray photographic plate, or X-ray sensors if we're using something sensible. So we'll probably make our plate out of some form of filtering material. So let's give ourselves something that represents filtering material. And what that's going to do is we will filter out. So this will filter low energy X-rays. Because we're going to dose someone with X-rays. There's no point dosing them with ones that will give them cancer but won't give you a picture. That's just stupid. Alright, cool. We've got that sorted out. Happy days. Now, we still then have the problem that this thing's going to get warm, and we've still got X-rays flying all over the place. So what we're actually going to do is we're going to tilt this a little bit. Okay, and by angling it, what we can do is we can ensure that the vast majority of electrons that arrive in here and produce X-rays that sort of target themselves predominantly downwards. Okay, so we end up with a greater concentration of X-rays traveling downwards. Then what we're going to do is we're going to embed this thing inside a block of copper. And this might take a minute for me to draw, because it's not that it's just like stuck inside it, because we still need access to the thing, but it's going to create a little heat sink for it. Okay, so let's put some copper in there. Fill up. And that's terrible, but it'll have to do. Okay, we're going to put some copper in this. Alright, that's going to act as a heat sink. Copper is a really good conductor of not just electricity, but also a really good conductor of heat. So some of the heat that's produced in our anode is going to flow. Shouldn't use red because you're going to think it's photons. So let's use purple for heat. So heat is going to flow into my copper. Alright? And then I'm going to surround the whole system in hydraulic oil. Okay, and again, what oil will do is that the heat that transfers out of my tungsten into my copper is then transferred into the oil. The oil is circulated and cooled, and that keeps the whole system from falling apart. Okay, like I said, this is all technical data as to how you would actually build the machine. The physics behind it is get a cathode, accelerate some electrons towards a tungsten target. What that'll do is it'll cause the promotion of an electron from the ground state to an excited state. That excited state has enough energy to produce an X-ray photon when the thing decays back down into the ground state. Those photons are then shot at a person and you get an X-ray. Job's a good one. Okay, so whilst we're here though, and we've produced some X-rays, maybe we can go a step further, because a standard X-ray is pretty good for letting you see, like that you've broken a bone in your hand or something along those lines. But maybe we want to see something a little bit more impressive. Maybe we want to build something like this. This is a CT scanner, with CT standing for computed tomography. Okay, where a tomograph is a sliced image of something. And what we want to do is we want to create, rather than a singular flat X-ray of something, we perhaps want to have a slightly more 3D impression of what's happening at various places. Okay, so this kind of ring structure is created here. Okay, we'll bring that over here for a little play about. Okay, so our ring structure is created here. Our patient lies on a bed that the ring was going to travel over. The little patient in here. Okay, so what we want here is we want two things. We want an X-ray emitter up here and an X-ray receiver over here. Okay, so we'll put the emitter in as a orange color, and we'll put the receiver in as a kind of blue color. Okay, and what's going to happen is an X-ray is going to come out of my emitter, travel through my patient, and be received on the other side. And that's going to create an X-ray picture, just as you normally would. Okay, but then what happens in a CT scanner is that the emitter and detector are moved around That's why they're on a circle. They're on the same circle together, so the whole thing moves at once. And an X-ray is taken from a different angle. And this whole process continues. You get X-rays from all sorts of angles all the way through that. The whole machine then moves, and you do the whole process again. It comes forward a bit, and you get another set of sliced images. And the result is that you can get X-rays from any given angle all the way through your patient. Now, you're probably only interested in a certain section of them. You could do a whole body CT, but that's a lot of X-raying. You're probably looking for a head CT or maybe an abdominal CT or a chest CT or something along those lines. You get slices and you run this machine over the area that you're interested in. You can see on this picture, you can see there's like little laser guide as to where you're aiming at this thing. Okay, because you're going to give this person a lot of X-rays at once. Unlike in a singular X-ray where maybe you think you've broken your hand, you get a couple of X-rays taken, and they can check out where the bone is, where the bone's broken. We're maybe looking here at trying to find something much more underlying, maybe in some soft tissue underneath. That way, you need lots and lots and lots of X-rays given to you. That's a huge radiation dose, but the process of giving you lots of X-rays is certainly better than the process of not giving you X-rays and you dying of whatever is wrong with you. Okay, so this is a CT scan. And basically what a CT scan does is it takes lots and lots and lots of pictures. Those pictures can then be printed out or put up on a board so that the surgeon can see lots and lots and lots of different sliced images of your head. So maybe you'd have set here, and there's your head, and there's like various sections of your brain, and if your brain looks like that, you're in all sorts of trouble. And then the next bit down has a slightly closer bit. So if you've got that, and then suddenly you find this really heavily darkened section, you go, oh, that's bad news, we'll deal with that. And the alternative is you can feed the whole thing into a computer, and rather than have to hold actual pictures up and look at them, they can come up on a computer, making it computed tomography. And this allows you to see huge numbers of slice images, flick back through them as if you're traveling through the person, or with certain advanced software, you can actually build a three-dimensional model of a person. Computer tomography, though, is fundamentally just lots and lots and lots of X-rays from lots of different angles that are then put together by a computer algorithm to build a picture that is a series of sliced images of the person. Those slices can be put together to build the whole person again. All right, so that's how lasers work, that's how you make X-rays, and that's how once you can make X-rays, you can make CT scanners. Not bad for a single episode, so I think I'll take a little wander off here, but of course, it would be remiss of me not to leave without mentioning that it is highly, highly, highly important that you remember physics rocks. It's true.